Assalamu alaikum. My name is Hafiz, Waleed Zahid, roll number 21 TE83 from Telecommunication Engineering Department, UAE TAXILA. Today we performed lab number 5, a representation of discrete time digital signals in frequency domain. In task 1, we have a code. In this code, this function calculates the discrete Fourier transform of the input signal x. It follows the formula for the DFT using the given sequence. It calculates the length of the input signal x of n. It creates a vector n representing the time indices from 0 to n minus 1. It creates a vector k representing the frequency indices from 0 to n minus 1. It constructs the DFT matrix W using the exponential term with negative imaginary unit. In second function, it calculates the inverse discrete Fourier transform IDFT of the input spectrum X. It follows a similar sequence of operations as myDFT, but with the exponential term using a positive imaginary unit. This code demonstrates the process of transforming signals into the frequency domain using the DFT and then back into the domain using the IDFTs. It's a fundamental concept in signal processing and has various applications in areas like communication, audio processing, and image processing. This is the output of the following code. In task 2, this function myDFT calculates the DFT of a given input signal x. It first determines the length of the input signal x. It constructs the DFT matrix W using the exponential term with a negative imaginary unit. The DFT of each signal is calculated using the myDFT function resulting in x1 to x11. This code demonstrates how zero padding affects the magnitude spectrum when calculating the DFTs of signal with different lengths. Zero padding increases the frequency resolution of the DFT, resulting in smoother and more detailed magnitude spectra. This is the output of the given code. In task 3, the discrete Fourier transform DFT of the signal x is calculated using the FFT function, resulting in the frequency domain representation x. The real and imaginary parts of the DFT x are extracted using the real and imaginary function, respectively. These parts represent the real and imaginary components of the frequency spectrum. The magnitude of the DFT is calculated using the ABS function. This represents the magnitude spectrum of the signal in the frequency domain. The original signal x, its DFT x real and imaginary parts, magnitude spectrum, phase angle, and the reconstructed signal xx are displayed to the console. This code demonstrates the process of transforming a signal between the time and frequency domain using the DFT and inverse DFT operations. It also illustrates how to extract useful information such as real and imaginary parts, magnitude, and phase angle from the frequency domain representation. In task 4, this code calculates the discrete Fourier transform of several signals with different lengths and plots their magnitude spectra, phase spectra, and power spectra. The effect of zero padding on the spectra is observed through the plots. This function calculates the DFT of a given input signal x using the formula for the DFT. Several signals x1 to x11 with different lengths and zero padding are defined. For each signal, the script calculates the using DFT using the myDFT function. It then plots three types of spectra: magnitude spectrum, phase spectrum, and power spectrum. The frequency resolution is calculated based on the length of the signal. Each subplot corresponds to a signal with the three spectra plotted side by side. The title of each subplot indicates the type of spectrum and the signal's name. The layout of the subplots is adjusted to improve readability. The plot helps observe how zero padding affects the spectra of the signal. Zero padding increases the frequency resolution, resulting in smoother and more detailed spectra, especially in the magnitude and power spectra.